Good morning, fancy meat computers. How's everybody doing today? Hope you're all having a good day today. Looks like the weather's gonna be nice today, so I'm gonna enjoy that because today's my day when I get to go to campus. So if you're interested in swinging by office hours, I will be on campus today. My room is ITB 102. So if anybody's having trouble with the assignment or anything. Or if you'd like to just, generally, talk about other things. Doesn't have to be assignment related. That's all I'm saying. Could be any number of things. But anyway. Good morning. Good morning. Good morning to all the students. Boop, 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 boop. All right. So, I guess we should just get into it, eh? So last time we covered quite a lot of ground. We talked about the call stack, what the call stack is. We talked about the difference between heap and stack memory. We went through some examples. And we talked about variables. We talked about the different types of variables that you can have, as well as what a type def is and does, and what an enumeration is and does. So it's kind of interesting. Whenever I talk to you about one of these concepts in C, something like enumerations, for example, the sort of baseline expectation of most programmers is that anything you can do in C, you can do in pretty much any other language. So you'll be... there's sort of a baseline expectation that pretty much any language is capable of producing enumerations. So it's... I always kind of think that C should be the first programming language that you learn, because it's the prototype of all object-oriented or imperative languages, more or less, derive, at least most of them, derive directly from C. So by learning C, it's like you're learning the ancient language from... It's like offering... If it were linguistics, it'd be like offering a class in Indo-European, which is, the hypothetical Paleolithic language that all languages are derived from, I think. I think I've got that right. At least in the sort of, Europe in through the middle of Asia type area. But anyway, so C is cool. I like C. Don't be a dope, consider the scope. Yes. All right, so we're going to talk then about recursion. Recursion is a bit of a tricky concept. If you've never heard of recursion before, this will be an interesting opportunity for you to expand your brain. Let me first talk about... Let me see. Are we talking about... No, we just get straight into the definition. So, let me preface this by talking to you about how... let me preface this with sort of telling you why recursion is important and why it's in this course, even though I know I don't need to teach it to you, right? But I'm going to teach it to you because one of the sub-goals that I have with the way that I've put this course together is to try to get you guys into a state where you're slightly less screwed for the rest of your degree program. That's sort of my design effort here with this course. And sooner or later, I think next semester actually, you're going to run into an algorithms course, I believe. So like software algorithms. So algorithms for me sort of hold a point of particular interest within all of the sort of software and software adjacent degree programs. Data structures and algorithms is like, if there's one course that I would consider the core course of the whole dang degree program, it would be data structures and algorithms, at least for like pure software engineers. It really is the course that turns you into a wizard. Before that, you are just a guy who knows how to program, and after you've mastered data structures and algorithms, you transform yourself into a programmer. Possibly even more so than like having the Linux skills, which are also a pretty good indicator of whether or not someone's really a programmer or not, or someone who just knows how to program. So, recursion it's a mental device which is used to structure certain types of algorithms and data structures. Question: do you have a course on algorithms? I'm pretty sure. I'm almost 100% certain that you've got a course on data structures and algorithms next semester. Mechatronics second year courses. Program overview. Oh, that's Waterloo. Pfft. McMaster. Interestingly, if you didn't know this, Waterloo also has a mechatronics program, and it kind of in their case arose from the mechanical department, whereas here it came into existence from the computing and software department. So that's why there's a fair amount of disparity between the Waterloo program and this program, because they have very different origin points. But yeah, I'm looking at it right now. Mechatronics 2 MD3, Data Structures and Algorithms for Mechatronics. Advanced programming with an emphasis on embedded systems, program specification and pre- and post conditions, loop and data type invariance, use of tools to demonstrate correctness. This sounds like a formal methods course. Selecting data structures for implementation of mathematical abstractions, finite state machines, automata and languages, lexing and parsing, algorithm analysis, time and space, modeling of graphs, relations, and corresponding algorithms. Okay, so that's a lot. There's a lot in there. But, yeah. So, yes. When do you learn enough code to become a nigh omnipotent god who can crush all who dare oppose you? When you learn Haskell. But Haskell doesn't have loops, it only uses recursion. Yeah, I actually have a problem like the problem that's happening in the chat right now of like McMaster being composed primarily of people who couldn't get into Waterloo. It's not so bad being second place. But I've got this one student who shall remain nameless, who's in a course that I shall not say, who keeps trying to tell me how to run my courses, and keeps wanting to be taking the course that is that they're offering at Waterloo, and it's kind of like, well, if you were good enough to get into it, then you wouldn't have to bug me about it, would you? Anyway, I shouldn't be mean. So recursion. So I mentioned this. The programming language Haskell, which is a very, very useful language. It's in the functional paradigm. The computer science people use it. I'm actually forcing them to actually use it for projects in 3MI3. And it doesn't even have loops. It uses recursion for everything. So recursion is a thing that you can use instead of looping. So what is recursion, then? Just so you know, guys, Mac was my first choice. Heart, yes. Mac was my first choice, too. But anyway. So what is recursion? Recursion is when a function calls itself. That's like the simplest way to explain recursion. But what recursion is mathematically is it's the application of an inductive, it's the translation of an inductive problem structure into programming directly. So we're kind of, you have to, Prof woke up and shows violence today. Yeah. Yeah, oh yeah, yeah, so Waterloo, the program is very good. The only thing you have to worry about is the suicide nets around the dormitories. Might drop. I'm not going to drop this mic. It's very sensitive. It's got a sensitive soul. So, anyway, so a recursive algorithm is a class of methods for solving problems where the solution depends on solutions to smaller instances of the same problem. So basically, this is the problem, this is the type of problem that you should apply a recursive algorithm to. If you have a problem, and you can make one decision, or make one calculation, and that results in the same problem but smaller by one step, that is a recursive algorithm. Because, essentially, you can nibble away at the problem until there's nothing left but, like, the final case. And if you can handle the final case, too, then the problem is solved. So, there are certain types of problems that are naturally amenable to a recursive solution, and you'll find recursive solutions exist fairly frequently in data structures and algorithms, because when you are building something like a tree, like a binary tree, you guys have heard of binary trees? You will by the end of my course, so don't worry about it if you haven't. But a tree, like if you have a binary tree, that's a recursively defined data structure because each node in the binary tree can be considered itself a fully fledged binary tree. So you can make like a decision about the top, go down one branch, you're presented with the same problem but smaller. So and the way that you solve these mechanically is by writing functions that call themselves. So, yeah. Yeah. Yeah, with McMaster's program, like, I feel like we strike a pretty good balance. Like, McMaster graduates are still, Waterloo is a very prestigious school. But McMaster is still a very good school, It's not like we're friggin' Brock. Jeez. Ah! Today is Professor throwing shade at every university. That's what today is. So here are a couple of problems that are naturally inductive. The definition of factorial. So you can define factorial by saying every number up to n multiplied together. That's one way of saying it. Another way of saying it is n multiplied by the factorial of n minus 1 if n is greater than 1 and 1 otherwise. Well, you know what? Okay. You know what? We're depressed, but only a little. Exactly. Your anxiety is recursive. If you can walk and talk, you can go to Brock. And if you can do it faster, you can go to McMaster. Yep. Yeah, so with the factorial, notice how the definition of factorial here is being used to define the factorial. If this were a linguistics class, you would get a 0 for defining your terms using circular reasoning. But this is not circular reasoning because of the structure of the natural numbers. See, when you take a natural number and you subtract 1 from it repeatedly, you will eventually reach 0 so long as n is not infinite. And since infinite n is not possible inside of a computer, any algorithm that you write which recursively subtracts 1 from something will eventually reach 0. Now, the problem, of course, is that when you use recursive algorithms, you are in effect making the call stack do all of this work. So it's easy to run into Stack Overflow problems if you're applying recursive solutions to too large a problem. But this is still, it is what it is. Another good example is the Fibonacci sequence. So the Fibonacci, and this is kind of this is how you naturally define Fibonacci. So the Fibonacci number n is the Fibonacci number n-1 plus the Fibonacci number n-2 for all n greater than or equal to 2 and 1 otherwise. This is logical OR, by the way. A recursive function is a function which calls itself. Notice that the Fibonacci number, you require calls to the Fibonacci function to calculate further elements of the Fibonacci function. So while loops are kind of like a recursive algorithm. Yes, the analogy to draw is with loops. However, it depends, like, a single loop is more like the factorial guy here, the factorial example. For this, you actually get like a branching of execution paths. So recursive functions will generally have an iterative case. The iterative case makes decisions, performs an operation, or in some way modifies the data passed into the function, and calls the function again with modified inputs. The inputs of subsequent function calls should travel in the direction of the base cases. Where do we actually define the Fibonacci function, though? I'm glad you asked that question, AJ. This is a sufficient definition of the Fibonacci function. You don't need any more definition than this. This is implementable. It's an inductive definition. Man, my 3MI3 class is tired of hearing about induction, I can tell you. So you have the iterative case. In the case of factorial, this is the iterative case, and this is the other iterative case. And the other case that you have is the base case. The base case. The base case. There we go. So, the base case does not require the function to call itself to return a value. Without a base case, your recursive function will call itself forever. There are programming languages like Haskell that use recursion exclusively as a replacement for loops. Question, like we are calling it within our definition, but it's hard for me to grasp how the computer knows what it is. It doesn't need to know what it is as long as it knows how to compute it. So let's whip up some quick C implementations of both of these guys, and hopefully that as long as that's not my next slide. It is my next slide. Okay, I'm gonna type it out anyway because that's useful. It's live coding. It's current pedagogical practice. I always think though that you should try to integrate it in less wait, is this topic 4? Okay. You should try to integrate it in, not like say, okay guys, now we're going to do live coding, Get it? Recursion.c. Okay. And Honk. Honk. All right, so Fibonacci. Well, first we need main. Include stdio.h int main. We'll just leave that there for now. So, the factorial. Let's do factorial first. Int factorial. Spelt with a K, because K is cool. Factorial. That's factorial, not factorio. It's like proof by induction in calculus. Yes. Yes, 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 Jack. Thank you. Yes! It is. It is. It is like proof by induction. Like, this is why it's called an inductive structure. So, factorial. If we need input, eh? So if n is equal to 0, still getting used to this keyboard. Return 1. Otherwise, return n multiplied by factorial of n minus 1. Save. And let's print. Let's just whip something up quickly. Int I equals 0 while I is less than 10. Am I solving? No, factorial, I asked you to do this with loops on the assignment, so I'm not giving you the assignment solution. Ha! I asked you to do this with loops. Except this time the computer is crying about it instead of us. Yes! The whole point of being a programmer is to try to outsource as much as you possibly can to the computer so you don't have to do it yourself. And that includes weeping. Just rending of clothing and gnashing of teeth. So, factorial of I. So this should give us the factorials of the numbers. Let's just factorial of is equal to that, and then we'll just print both I and factorial. There we go. This should be a C program for sure. GCC recursion.c. There we go. No errors! Ha! Compiled first time, no errors. Let's see if I've got any warnings. No warnings! Ha! Your professor is a perfect C programmer. A.out. Oh! I got the factorial right, but I forgot that I need to not have an infinite loop here. Ha ha. There we go. So there you go, factorial of 0 through 9. Are recursive functions or loops more demanding on the computer? Good question. Recursion is more demanding, but using recursive algorithms, you might be able to get like sneaky algorithmic improvements that compensate for the fact that factorial, like recalling a function call is more expensive than a loop, right? Because you have to create a whole new stack frame each time you call a function. So you know, it's to some degree there is more expense involved in performing a function call because you have to add something. You have to add a stack frame, and you have a limited number of stack frames you can add, so you have a limited recursion depth, especially in C. But there are clever algorithmic things that you can do with recursion that compensate. It depends on the situation, but we're going to see some algorithms coming up in the course that use recursion that are awesome. What's the keyboard shortcut to terminate the code? Control-C. Control-C. This is why like copy paste doesn't work in Bash. It's because Control-C is mapped to terminate. Control C. And I didn't fix the infinite loop. I just killed it. The other thing you can do is use htop and find the process and kill the process using htop. But F10. What? Oh, it's mapping to there. All right, I'll just close this. Close. Fake news. All right. So that's factorial. Notice, like, I'll do a trace. Wait, maybe that's not useful. Yeah. So let's do Fibonacci. Int fib int n. Now, Fibonacci is interesting because it's very, very easy for it to blow up out of control. But as we'll see. But if n is equal to 1 or n is equal to 2. All right, no, wait, is it 0 and 1? Let's see. It's 1 and 0. Okay. Some people like doing, like, Fibonacci of 0 is 0. Apparently. It works, apparently. But, like, if you do 0, 1, 1, 2, 3, like, that sequence still works, right? Because 0 plus 1 is 1, and 1 plus 1 is 2. In my 3MI3 class, there's a fair amount of... There's a pretty hefty contingent of people that think that it's too cool that you can start this Fibonacci sequence at 0, that should be the new definition. To which I said, you should start a change.org petition. So if n is 0 or 1, then we return the value 1. This is the base case. Otherwise, we return Fibonacci number n minus 1 plus Fibonacci number n minus 2. There we go. So you can see that from a programming perspective, this is like a very, very close correspondence to the there, thank you, to how we inscribed our inductive definitions, right? It's like you can see the exact correspondence. Calling the function, multiplication operation, that line translates pretty much exactly here. This line translates pretty much exactly there. And the if statement is just controlling these cases here, right? It's like a direct translation of these inductive structures into code, right? So Fibonacci of that is, and then we change this to fib. There we go. So this will be fun. Let's compile that up. Oh, what do I got? Line 16. I used the wrong bracket. That'll get me every time. Actually, I think that's the first time I've ever used not a curly brace when I meant a curly brace in my entire life. There you go. A dot out. There you go. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. There you go. So, I don't know if this was already said, but does recursion create a call stack, which is then returned as the final value is in the main function? Yeah, so I'll take this guy and put it into CTutor so that you can see the call, what's going on in the call stack. But I just want to show you how easy it is to break this thing first. So that's 1 through 10, or 0 through 9. Let's see what happens when we try 0 through 29. I need to recompile. We're still going. Okay, I need... I need more power. Wow, this is... There, okay. Ah, there we go. See how it's slowing down? Ha ha. Okay, just so you know. Okay. Just to let you know, I'm super impressed. Possibly this is because I have a new... This is probably just because I have a new computer. And my new computer is super fast. But, like, I'm used to, like, this case here taking, like... Or, well, actually, like, 32 used to take, like, a full 3 seconds in Python. So it's like a combination of C just being faster than Python plus my new computer. I'm very impressed by what my new Fibonacci limit is. But, yeah. So, let me just... Yeah. See how it's taking longer and longer to calculate these things? Generally speaking, each one of these numbers that I'm calculating takes twice as much time to calculate as the previous one. Right? What are the specs? I don't know. It's that's not important. It's like it's AMD Ryzen 7 5000 series. It's like a 16 core. It's a really good CPU. Ha! And then I hit overflow. Ha! There we go. So so I've hit the overflow point, so, like, no integer past this point is going to be interesting or useful anyway. But let me show you how to fix that, actually, or at least temporarily offset it. You can use long ints instead of ints. And LD, I think. I think that'll... Yeah. Does it tire out the computer? Well, I'll show you what's actually going on, right? So, yeah, okay. And I'll explain what the concept of overflow is. But where did we overflow previously? We overflowed at 46. So I'll show you how using long ints you can get more. Although, no, that's still good. So, all right. I'll tell you what overflow is first, right? So get your calculator out, right? Type 2 to the power of 32, right? Divide by 2. Hypothetically, that's the largest number that you can hold. So let me just see if I've got 2,147,483,648. That should, in theory, be the largest positive integer that we can hold. So let me see if that's... Let's see. Are we got with... So that's thousands. That's thousands, millions. No, we should be... Wait, millions? Billion? Yeah. Okay. So we did hit our overflow limit. So integers by default are integers by default are 32 bits. So if you have a number that is larger than 32 bits, it doesn't fit. So what happens is it just wraps around. It's like the largest positive integer. If you add 1 to it, you get -1, and then it counts down or counts up or something like that. Or it starts counting up from the lowest possible. I forget. But yeah. Isn't that just 2 to the power of 31? Yes. So you can see, it took a while to do it, but it managed to actually produce these numbers accurately, because when you make something a long int, what you do is you give it an extra 32 bytes of space to be able to store stuff in. But you can... So that's what overflow is and what it looks like and what it does. And it can be a tricky bug to spot, right? Because basically, everything will be going along fine, and then eventually you get some stupid random negative number that doesn't make any sense and is not correct. And that you'll have hit overflow. Yeah. So, Yeah, so the reason it's 2 to the power of 31 is that 1 bit is used to be... 1 bit is used to control signedness. It's actually... Well, that's how it works in float. It's actually a little bit different in... numbers are stored in what's called 2's complement. But yeah. Yeah, so as your colleague notes, if you bring your the factorial algorithms that I asked you to produce on the first assignment, if you try numbers past 13, you'll end up with overflow. And like some people were asking about this, and it's like, no, actually, it's expected. You can get around it. You can delay that somewhat by using long integers, but you won't be able to delay it forever. That's a big difference between C and Python. In Python, they just keep allocating your integers space so long as you, so like it just keeps giving you more memory to store this one ridiculous integer. Whereas in C, there are hard limits to the range of integers you can store inside of your data types. Yeah. Yeah, it's 2 to the power of 31 minus 1. Yeah, that's correct. Yeah. We have some slides coming up later on 2's complement. Well, this kind of bit whacking type stuff. But anyway, I want to get back to Fibonacci because we're going to finish recursion today. But it's important, like it's a very important concept, so it's worth taking a little time to go through it. So, here's CTutor. There we go. We'll just knock this down to like 5. Because, this isn't my computer, so I don't feel comfortable abusing it. You can call me a wimp if you want. I won't mind. Okay, there we go. So let's do this one. So you'll notice how much time it's taking to execute each of these, right? So let's calculate the Fibonacci number of, there we go. Let's calculate the Fibonacci number of 3, right? So first thing that happens is it's not 0 or 1, so we get into this case, right? So what we need to do is we need to first calculate Fibonacci number of n minus 1, which is 2. That requires calculating the Fibonacci number of 1. That one does actually return 1, so we can close off this stack frame, right? Then we need the Fibonacci number of 0, which closes off that stack frame, because that's a base case. So we now know what the Fibonacci number of 2 is. But then we need to calculate Fibonacci 1, it's the base case, etc. And then we know what 3 is, and then we can return that back. All right? So it gets a little more interesting if we do something like Fibonacci of 8. So you know what? I'm going to use my favorite Linux Paint program to draw something here. Height, width, 12. Create. There we go. All right. So this is what's going on here, right? When you have... So let's say you wanted to calculate the Fibonacci number of 4. That's probably too... Let me increase the size of that, right? Let's say you... Well, let's do 5, right? To calculate Fibonacci of 5, you need to know 4 and 3, right? To do 4, you need 3 and 2. To do 3, you need 2 and 1. To do 2, you need 1 and 0, right? 2 needs 1 and 0. 3 needs 2 and 1. 2 needs 1 and 0. So the sort of dumb, straightforward way of doing Fibonacci, which I have illustrated to you, you'll notice there's a fair amount of redundancy. Like, you can see how many times we are recalculating what the Fibonacci number of 2 is, right? It's the same case. It's the same. We also recalculate what 3 is a bunch of times. And I realize this is like the messiest thing in the world. I hope you'll forgive me. But, because there's so much redundancy in the way that it's calculated, basically, every time you increase the number, increase the Fibonacci number you're trying to create by 1, you're doubling the number of cases that have to be calculated. But yeah, as one of your colleagues points out, this is a binary tree. So your call becomes a binary tree instead of just like one after the other. Which is why when we were executing all of those cases, by the time we got to the mid-30s, you could visibly tell with our stupid, slow human meat brains that each case was taking about twice as much time as the previous one to calculate. Yeah. So that's why it's so slow. So you got to be careful with recursion, because it's easy to set up stuff that's not actually, it's bad enough if you did 2 recursive calls for every 1 call. Imagine if you did 3 or 4, how badly that would blow up, right? But yeah, so we did that. Final notes about recursion. In C, all of our function calls are going straight into the system call stack. If the recursion depth is too great, you can easily cause stack overflow. This is particularly true of recursions like Fibonacci, which call themselves twice. Well, actually, that's not exactly true, now that I think about it. The thing about Fibonacci is that although you've created all of these different branches, the branches are still being calculated one at a time. So the depth of the binary tree is limited to whatever n is, and any modern computer can certainly handle up to 40 or 50 function calls in the call stack. That's fine, So that's not quite... So what you have to worry about there is runtime. It's not an efficient algorithm. You can make it more efficient by using what's called a memo to store intermediate results, right? If you store what fib2 is, then you can refer to that. You don't have to keep recalculating it, which will save you a hell of a lot of time and basically turns that big O 2 to the n algorithm to a big O n algorithm. We're going to talk about big O at some point when we talk about algorithms in a bit more depth. But yes, you often, when you're programming, have a trade-off between holding memory and using more runtime. And if you're using a lot more runtime, sometimes you can improve that a lot just by allocating a little extra memory. But yeah, so everything a loop can do, recursion can do, and vice versa. So what we just did, we can also write algorithms that use loops that do the same thing. And any loop can be a recursion. However, again, it comes down to how the data structures have been defined. Sometimes recursion is going to be the naturally occurring solution, right? It's like the problem already has an inductive structure. It doesn't require any mental effort to do a direct recursive algorithm, whereas it requires more mental effort to construct a loop-based algorithm. So recursion has its uses, it has its place. Some programming languages use it for everything exclusively. Yes. Many useful data structures have recursive definitions, such as trees, heaps, lists, and linked lists. We will get to these eventually when we learn about structures, which is towards the end of the course. So yeah. Any questions? Does this cause problems for people like, say, astronomers? The overflow thing. Or do they use Python? They would probably just use Python. It probably caused problems for astronomers in the 70s. We have 5 minutes left in class, which is really just enough time for a preview of coming attractions. But the next, you can see I've got a image about Big O coming out for the next set of lecture slides. There we go. Arrays and introductory algorithms. Oh, I need to regenerate this. I have a question about floats. Give me a second to type it out. Okay. But we're going to talk about arrays. Arrays are, just quickly, how many layers within a D&D campaign can you go? Well, that depends on the stack size of your DM. I find normally humans have a, better than you'd think. I'd say humans probably have a stack size of, 6 to 8 tasks. But, yeah. Role-playing an orc, role-playing an edgy princess, begrudgingly role-playing an elven archer. Yes. An elven archer who's having to sit through an Underdark campaign because the DM just loves the Underdark, but nobody else does. I think it's called the Underdark, right? Yeah. D&Dception. Ha! That's good. So. I'm going to do, a couple of slides here. So. I see data arrayed before me. In Python, there are many data structures that you have to choose from. You got tuples, lists, dictionaries, sets, and strings, and that's if you don't want to make your own by using classes, right? Okay. I will answer your question about floats in 2 minutes from now. In C, the only data structure supported natively is the array. If you need something more complex than an array, you have to either find a library defining it, or define it yourself. An array is a contiguous segment of memory, which may be accessed via linear indexing. All elements of an array have the same type. This is a big difference from Python. In Python, a list can have any number of types going on in it. In arrays are what we call monotyped. They have one type. Everything in it is one type. Arrays use zero indexing, and the reason for zero indexing is something that we will discover over the course of this course once we get into pointers. Arrays are static. The size of an array does not change during execution. Now, this is also a big difference between Python and C. So arrays in C are kind of like you take some of the things from lists in Python. You take some of the things from tuples in Python. Like with a tuple in Python, you can't change its size after you've created it, and you also can't modify its values. With a list in Python, it can grow or shrink dynamically, and you can modify its values. In C, an array does not change its size after creation, but you can modify its values. I'll recompile it. Oh, it's like that on the yeah. Sorry, sometimes I forget to compile it twice. Yeah. Good. So we're going to talk much more about arrays next time. Syntax is about what you'd expect, though. Well, it's a little bit different than what you'd expect. We'll get into it next time. So, question. So in assignment 4, I think we were doing powers for a float. For some reason, wherever I get an answer, it is only accurate to the first 2 or 3 decimals. Oh, this is a question about the assignment. Even if I change from floats to doubles, I don't see a change. Why does math become inaccurate? There's no dot append in C. Absolutely, there is no dot append in C. There is no dot append in C. That is correct. I will say it a 4th time, just to sink it into everybody's brains. There's no dot append in C. So why does the math become inaccurate? Well, it's because floating point numbers aren't accurate. Let me show you something real quick. Python. I don't know if you've ever seen this. I'm doing it in Python because it's faster. So if you add 1, 3, 6, 7, 8. Wait, is that 8? That's 9. One more. So if you add 0.1 together 10 times, hypothetically, the answer that you should get is 1.0, right? That's not actually what you get. You get 0.999999999. And the reason for that, it's kind of complicated, but so you know how if you have 1/3, if you write 1/3 in decimal, it's an infinitely repeating set of 3s. But if you so 1/3 written in decimal is an infinitely repeating set of 3s, but it wouldn't be if the decimal was base 3, right? If it was base 3, then you'd be able to represent it with exact precision. 0.1 cannot be represented in binary decimal, in fractional decimal, fractional numbers. So everything in the computer is binary, including the real numbers. So basically, the only decimals that it's possible to represent with absolute precision inside of the binary system are ones where they would be a fraction that would have a power of 2 as the base, right? Another way of saying this is that if you want to represent a base 10 number in base 2, some of them are going to be infinitely repeating decimal, like infinitely repeating or infinite series of decimals. They cannot be represented in finite precision. So the computer does the best it can. It represents as much precision as it can. This is not exact precision, and it's pretty small, but with certain types of operations, that error it'll come out. So like format I think I'm remembering how to do this correctly. 0.60 f. Yeah. So 0.1 is actually 0.1.00000, etc., 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 and then you've got this tail, which is not like this is what the number actually is. So why you should have a bunch of these, add them together, and get it to be less than 1 is an exercise I will leave to the reader. But basically, yeah. So, okay, that makes a lot of sense. Wait, then how do calculators work? So long as you're not like, so what's the number of numbers you have on your calculator, right? It's like the number of numbers that they represent on your calculator: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 digits. So your calculator does things to 10-digit precision. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So your calculator only doesn't even do this bit, right? But I'm going to guarantee you that this is also the way that your calculator does things, because this is like the IEEE and the IEC have standardized this notation for electronic devices. So this is the same way your calculator works. It's just you're usually operating in precision that's so high that it doesn't matter. But yeah, this is also how your calculator works. Yep. So, let's see. In Python, you could make an empty list and then append to it. How would you be able to do that in C? You can't. You can make an empty pointer and then dynamically allocate memory to that pointer, but it's not easy, and it's likely to end up in seg faults. You should, so generally speaking, in C, the method that sort of novice programmers will use is to allocate as like more than you think you would need, and then just operate with a tail on your array that you don't necessarily need. That's like the quick and dirty way to get it done. But the proper way is to use dynamic memory allocation, which we're not going to know how to do until we know how to use pointers. C already took away for loops, but append too? Yes! Yeah, you guys had no idea how good you had it. Hey? I think you can initiate the array with X elements and fill it with garbage as data garbage data as placeholders. Garbage data makes a terrible placeholder. You should use a placeholder that, like -1 or 0, that you can tell what it is. The other way to do that is to keep track of, like, hold a variable that tells you how much of your array is junk, and like it's valid up to the value of the variable X. That's another way to do that. C has loops. They're just different. C only really has one loop that's sugared differently. There is no for loops. There is no in keyword. That is also true. There is no automatic searching operation. We're gonna actually we have a searching operation that we're going to talk about actually. Yeah. Well. So one of your colleagues indicates the 0+1 trick works on the calculator, and it's like, yeah, that's true, because let me show you something. It's because this is giving you more precision than the calculator does. Right? Like, if the calculator is made to round to, like, 10 decimal places, then this would come out, right? It's like, round that to 10 decimal places, you know. That would work. In a calculator, it'll be, like, rounding it before it's displaying it, right? Oh, okay. For loops. Okay. Pedro, I need to clarify something. For loops in C are very, very different from how for loops work in Python, right? A Python for loop allows you to iterate over a data structure. A C for loop is really just a rewriting of a while loop, right? You're taking the initializing condition, you're taking the initializer, the condition, and the update, and you're putting them all on one line. And that's what a for loop is in C. But what these guys are complaining about when they're saying C doesn't have for loops is they're saying C doesn't do for loops in the same way that Python does a for loop, which is very convenient. Some of the later C, like some of the other C iterated languages, like C#, for instance, has a for all. No, it's like a, what do they call it? It's like for all loop or something like that, which essentially functions like a Python for loop. Or for each. It's called for each. So for each element in this specified data structure, do X, Y, Z. C# has it, but C, you won't find it. It's just loops that have been rearranged to be slightly easier to use. It's like the Java for loop. Yeah, I think so. Yeah. So, running 1.303 to the power of 5 on C on my calculator gives slightly different results. How do you know which one is correct? By doing it by hand. And then picking whichever one is closer. Yeah. There have been, I've received miscellaneous reports of the POW function being problematic. I'm not sure if this is a problem, like, between using Linux and Windows. I don't know if this is a problem, like, with VS Code. It just, like, the POW function seems to not work somehow for some reason. So, yeah, not sure what to do about that one, to be honest with you. You could re-implement power, which works as long as the power you're raising things to is an integer, which I can't remember if it is, but yeah. Well, we'll see. We'll see how it goes, so to speak. Alright. Anyway, I'm gonna log off at this point. Again, office hours are today, if anybody wants to drop by. Take her easy, folks. I will see you next week. Bye-bye.